Okay, let's go over some tips. These are the things that are easy to screw up when you have a semester final or a big exam or something when it comes to Calc AB. Okay, so I've made 11, okay? So the student I'm talking to, these are the ones that I think are the biggest concerns for me. This doesn't mean that if you get all these, you're going to ace this thing. But these are the things that you should have in your wheelhouse. You should be able to solve, and sometimes you struggle with. So let's see what we can do. Okay, so let's look at them in order here. I just kind of wrote these up. Number one, this is an occasional concern. Recognizing the difference between setting an equation equal to 0 and then plugging a number in with a variable. We've seen problems before where you take the derivative of a function, and then let's say, for instance, and I'm going to see if I can come up with examples here. Let's say for number one, let's say we want to find the equation of a line that is parallel to a line with a slope of 3. Okay, so let's say they give you that. Let's say, and I'm just making up the equation, let's say it's 3x squared plus 6x minus 1, and we want to know the equation of that line that is parallel to a line with a slope of 3. So what we have to do is take the derivative. And on this one you can see we just use power rule, 6x plus 6. And now here's what I'm talking about. I know I've seen it before where you might think, oh, I'll just plug in 3 for here and solve. That's not the case here though. Remember, f prime of x gives us this new function, this new equation that will give us the slope for any particular x value. This isn't an x value, this is the slope. So on this sort of problem, we would want to set it equal to 3. And we would be solving for x. Okay, 6x equals negative 3. I think you can see what's going to happen here. X is going to be equal to negative 1/2. If you had put in 3 for x, you would have gotten 24, and that would have been completely different than a negative 1/2. Okay, notice how I said find the equation, right? So this would help you find like the x-coordinate of the point. We'll come across one of those problems later on here, okay? Okay, number 2, use the negative exponent to take the derivative and then undo it. You're good at this, but I still see occasional hiccups when it comes to actually taking the negative exponent. So let's say we have to take the derivative of a particular function, okay? I mean, it can be something like 5 over x squared, okay? So let's say this is f of x, and we want to find the derivative of this. If you leave it in this form, you got to use quotient rule, right? Down d up minus up d down over down squared. That will work. If that's how you want to do it, okay. Me personally, it's simpler to rewrite it like this. 5x to the negative 2. Notice the 5 stays on top. This x squared, which was on the bottom, we're now going to bring it up to the top. So think of this being a little indicator that it is in the other world. It was down here, now it's up above, because this is the same thing as 5x squared over 1. So the reason we do this is if now, say we want to take the derivative, d dx of each of these, d over dx. Now it's not too hard. We can use power rule. 5 times negative 2 is negative 10. And notice what happens here. We're going to subtract 1 from it. That doesn't mean it goes closer to 0. It means we subtract 1. A negative 2 minus 1 is negative 3. And the point I had is, once you take the derivative, now change this back. Get rid of this negative exponent. Rewrite it where that coefficient stays on top. We're going to move this to the bottom but make it a positive 3. Okay, so the derivative of this is this. If you use quotient rule, you do get the same answer. You can use that. I just personally think this is faster. Okay? And the reason you change it back is if, say, you have to set this equal to something, then it's easier to find x. Then you can multiply both sides by x cubed. You don't have to worry about getting involved with a negative at that point, because that can be confusing. Okay. Number 3. Infinite limits is equivalent to, I guess I could use this, it's equivalent to horizontal asymptotes. You've been asked some questions about infinite limits. Okay? They might ask you, what's the limit as x approaches Now if this says as x approaches 0 or x approaches a certain number, then it wouldn't be an infinite limit. We're talking about it approaching infinity. Either positive or negative, but for the most part, it doesn't matter in these problems. And in advanced algebra, you learned about horizontal asymptotes. Remember how horizontal asymptotes work. You've got a particular function, okay? And as it goes all the way to the right or it goes all the way to the left, it usually settles on a particular asymptote. That's the case if the degrees work out. I think you understand how the degrees work out on this problem. But let me say I come up with some problem, say x to the 4th plus 1 over x to the 5th minus 2. Okay, something like this. Look at the degree on top and degree on bottom. Okay, if the degree on top is smaller than the degree on bottom, okay, if the bottom is bigger, then that means your limit is going to be 0. Give you a couple more examples here, okay? Let's say the degree on top is bigger than the degree on bottom. Okay? This will be, does not exist. We don't have an infinite limit when the degree on top is larger than the degree on bottom. And then of course the last example, and I think you're good with this, but let's go over it anyway. Let's say they are the same. X to the 4th plus 1 over x to the 4th minus 2. These are actually irrelevant. They don't really matter when we talk about infinite limits. But you look at the degree on top and the degree on bottom, and if they're the same, your limit is going to be this divided by this. It's going to be the leading coefficient on top divided by the leading coefficient on the bottom. So for this one, it's 1. Say I had the number 3 here, it would be 1/3. Say I had the number 5 here, it would be 5/3. If I had a negative here, it would be a negative there. Okay? Hopefully you can follow along on that stuff. Hope that answers questions for you there. Let's look at number 4. Okay? Look for clues within each question and ask yourself which derivative to take. I don't have any examples to show you right now on this. I guess what I'm pointing out is, let me see if I can find one real quick. I guess I don't really need to show you one, but when you get the original paragraph, okay, the information they give you at the beginning of the problem, when I'm talking clues, if they say in terms of point of inflection, you're probably going to find the second derivative of the function. If they give you f of x and they're asking for points of inflection, you're going to want to know, you're going to want to find f double prime of x, okay? So for any f of x, if you take the first derivative and you set it equal to 0, that's going to give you critical points. So if they talk about critical points in the problem, you know you're going to take the first derivative and set it equal to 0. If they talk about critical points, if they talk about particular points on the graph that have a slope of 2, you're going to take the first derivative and set it equal to 2, like we talked about earlier in this video. Okay, for f double prime of x, this now deals with concavity, either concave up or concave down. This is points of inflection. And on a lot of these problems, you end up having to do a sign chart. Okay, so let's say we're doing a sign chart for this. If there was a question where they say, over what interval is f of x increasing? When you see words like increasing or decreasing, you should think first derivative. You should set it equal to 0 to find critical points, and then you come here. And let's say, for instance, you got critical points of 2 and 5. This is just an example. Now we're going to want to check this interval, and this interval. And we'll want to compare it to the equation f prime of x. So maybe we check f prime of 1, and maybe we get a negative value. Let's say we check f prime of, 3, and maybe we get a positive value. And here we check f prime of 6 and we get a negative value. Usually it goes like this. For the most part, it'll switch from positive to negative for negative to positive and keep going. You should still keep checking because you might end up having what we call a double zero or a double root. But usually it's like this. And when you draw out your sign chart, on the bottom you put what value you got for this particular equation. Okay, I know you missed this part a lot, but you got to write this here. Then above it, talk about what it means in terms of f of x on top here. So for this, it means it's decreasing. Positive means increasing. A negative f prime means a decreasing f of x. This same idea works if we were doing a second derivative test. We never really do third derivative tests. We don't talk about jerk, which as you know is f triple prime equals 0. We don't really talk about that, okay? But let's say again, I'll just make up numbers, -2 and 1. Here we'd find f double prime of -2, okay? We'd find that. And whatever value we get, it's kind of tight a space there. Whatever value we get, is it positive, is it positive or negative? Let's say we get a positive here. For f double prime being positive, that means that f of x is concave up. If it's a negative, that means it's concave down. Positive, concave up, and then that helps you answer questions on intervals. But look at the clues in a particular problem, and I'm not even going over every single clue. But you know when you're reading a paragraph that they give you, some of that information is just English to make it flow well. Other things give you a really big hint. So make sure you follow along in that regard. Number 5. Think about continuous or discontinuous versus differentiable or non-differentiable. I'm asking you to recognize the difference between those two, okay? I don't think this is much of a problem for you, okay? But it does kind of come into play when we're talking limits, for instance, okay? If it's continuous or discontinuous, you should know discontinuous functions have like a jump, like this, okay? There's a discontinuity here at x equals 1. We'll call it 1 here, okay? If there's no breaks, it's continuous. Now here's an example of something that is continuous, but not differentiable. We'll look at an example of an absolute value graph, okay? This has a continuity. The domain goes from negative infinity to positive infinity. The x values go all the way to the left and all the way to the right. The range on this one does not go from all the way down to all the way up. It's whatever this value is. If we said this ordered pair was 2, -2, then the range on this one would be from -2, including big bracket, okay, squared off bracket, all the way to positive infinity. This is an example of something that's continuous, but it's not differentiable. And how can you tell? Well, what's the slope of the tangent line there? Who knows? We don't know. It looks like it's somewhere between 1 or -1 and 1. But any of those particular lines could go through at that one single point alone. So we call that not differentiable. Okay, something that's differentiable is curvy. It's smooth. It doesn't have cusps or corners. It also doesn't have vertical places where the tangent line would have an undefined slope. Okay, this would be not differentiable. You rarely see it, but I think, for instance, f of x equals the cube root of x. I think that's what it does. If you zoom in closely, you'll notice that right here at 0, it actually gets perfectly vertical. Okay, and to prove that, you could take this, I'd rewrite it as x to the 1/3. I'd take the derivative of it, and I'd set it equal to 0. And once you end up doing that, you'll recognize that you get a do not define, or does not exist. You get 1 over 0, of something over 0. So that's kind of proof there. Number 6. If it's hard to find a derivative, use the chain rule. Use substitution is one way to use the chain rule. Okay, it's helpful. I'll come up with an example here. Okay, I mean, sometimes you can just tell. Like if I want to know the derivative of 3x squared, that's a breeze. It's 6x. Okay. If I want to know the derivative of 3x squared sine x, I'm going to use product rule. I can split it up like this. Derivative of the first times the second plus derivative of the second times the first. That's not really a problem. But let's look at something like this. Sine of 5x. Now this is something where use substitution comes in handy. Some people might recognize right away what to do. I'd say go with use substitution. Remember, the reason we do use substitution, the reason we need a chain rule, is when we have a composition of functions. Look what's going on here from the inside out. We've got an x value. We multiply it by 5. So just 5x, well, I know the derivative of that. But then I'm asked to take the sine of that thing. It's almost like the inner function is 5 times x, and the outer function is sine of that thing. When it gets complex like that, when we have in essence an f of g of x going on, it's helpful to use substitution. If u equals 5x, du equals 5. Now we can rewrite this in terms of u. We'll just call it y for now. We'll call it sine of u. And if you want to find the derivative of y, or y prime, whatever you want to call it, this is going to be cosine u du. Do not forget that. Do not forget that. And then you can plug in what you know. There's my u value, cosine of 5x, and it's times 5. I can now rewrite this as 5 cosine 5x. You do these enough, you might feel like you don't even need use substitution. You see this and you say, oh, okay, well, it's cosine of that thing times the derivative of that thing. That is actually true. If you're good like that, go with it. Okay. Sometimes we see them even nested more, but I haven't seen that in any review, so I'm not going to be too worried about that at this point. Okay. I think this is all you're going to need to deal with. Just so you know, if you want to find the derivative of a composite function, this is basically the chain rule that I'm giving you. It's the derivative of the outer function with the inner function intact times the derivative of the inner function. Think about how this relates to what we did over here. Okay, we took the derivative of the outer function, the f prime of that 5x. So the derivative of the sine of 5x is cosine 5 of x times the derivative of that inner part. The derivative of the 5x is just equal to 5. I just made this look this way because that's how you typically see it in math texts. That's the idea number 6. Moving on. And please remember, you can keep pausing this, rewinding it, fast forwarding it, whatever you need to do to remind yourself of what you need on your exam. Number 7, if we're finding the equation of a tangent line, use point-slope form. That's a sticking point with you lately for some reason. Okay? If we got to find the equation of a tangent line, well, how do you express an equation? You know, you can express it like y equals mx plus b. If it's a multiple choice problem, they might give you 5 choices in this form. They might express it in standard form, which is ax plus by equals c. We capitalize those for some reason. Okay? This is really good when we're combining particular equations, but it's not really helpful for a line. Still, they do it sometimes. But point-slope form, y minus y1 equals m times x minus x1. This is the slope, and this is the coordinates of the point that you find. Okay? So slope is up here, and then you plug in the ordered pair there. So if you see a question where they say, find the equation of the tangent line that has this point, and maybe they only give you the x value, you have to go to the original equation to find the y value. And then they tell you it's got a slope of 1/2. Or they tell you it's parallel to this particular line. Well, if they give you that line, then you find the slope and you recognize that this will have the same slope. If they say it's perpendicular to a line with this equation, then you find the slope of that line, and you recognize the rule about slopes of perpendicular lines. They are opposite reciprocals of each other. If one line has a slope of 1/2, a perpendicular line will have a slope of, well, it's negative 1/2, but then you flip it, it's negative 2. Okay? So I want you to be careful on that. Number 8. Looking for relative extrema within a given interval. Test critical points and interval boundaries. Okay, I'm talking about with a given interval. We're looking for like the maximum value within something. From t equals 1 to 3, and then they give you a function, and you got to go ahead and find like the maximum value. There's usually 3 numbers you'll then have to test. If they tell you, I'll just say t. Sometimes there's an equal sign, sometimes not. And they give you f of x, whatever it is, blah, blah, blah. Okay? What you'll have to do is take the derivative of it, whatever you get here, set it equal to 0, and find your critical points. And you're probably going to you might get a couple of them, but only use the ones that are within the boundaries they gave you. And then if they want the maximum value, you're going to have to test f of 1, f of 3, and f of whatever critical point you got. You'd have to find each of those. Or if you're looking for maximum value, you'd plug in back to the original equation, f of 1, 3. Whichever one is the highest value, Okay, so let's say this is 10, let's say this is 8, and let's say this is 6. That would be the highest one. How can a critical point have the lowest value? Maybe it's a relative min. Okay, maybe we have something that looks like this. Maybe this is 10, this is 8, and this is 6. That's how it's possible. You don't know if a critical point is relative max or relative min unless you do a sign test. And if you see a problem where they ask for proof that you have a max or a min, the proof is multi-layered. It's good to show a sign chart, okay, f prime. Let's say your critical value is here. Let's say you find that this is a negative and this is a positive. That means in terms of f of x, this would be decreasing, this would be increasing. And then if this is a free response problem, you should write more out, okay? You should say, and I'm not going to write it down, but listen. You should say, this is the critical point, or this is the highest value, okay? And you'll say that, and then you write because f changes from decreasing to increasing at that point. Or you can say f prime changes from negative to positive at that point. But you're going to use the word changes. There's a change. In terms of f prime, if it goes from negative to positive, that means negative slopes to positive slopes. In terms of f of x, it goes from decreasing to increasing. You can see here I'm going to have a relative min because f of x goes from decreasing to increasing. Write that out. It's like a single sentence. It's not that long. A particular point is a relative minimum because f of x changes from decreasing to increasing at that point. That's enough. But you do need to show that. I believe teachers like to see this, but they really need to see the statement. That's what gets graded. If you don't show the statement and you do show this, you'll probably get like half credit. You're not going to get all the credit that you want. Okay, moving on. Got 3 more. If you're solving a limit, okay, make sure you plug in what they have the x value going to as a starting point. But recognize 0 over 0 is not an acceptable answer. And then you got to try to factor. And we're doing limits like that. Okay, now this is not an infinite limit. Let's say x approaches 2, okay? And let's say they give you something where x minus 2 is in the denominator. And then on top, I should come up with something really obvious here. Okay, this is an obvious one. X squared minus 4, okay? Because I recognize this is going to factor, and one of the factors is going to be x minus 2. If you plug in 2 right now the way it is, you get 0 on top and 0 on the bottom. 0 over 0 is not an acceptable answer for a limit. It's not even defined in terms of math. You can even ask your calculator what's 0 over 0, and it's going to go, I don't know what it tells you. It tells you an error, though. It doesn't like it. Here, I'll even ask my calculator. Hey, calculator, what's 0 divided by 0? It says error divide by 0. I can go back and, well, change it, but it doesn't help now. Divide by 0 error. We can't divide anything by 0 and still have it defined in terms of math. So what we do now is we look to factor, okay, primarily. That's the difference of squares. Hopefully you recognize that as x minus 2 and x plus 2. If I do that and cross them out, and now I can rewrite this as a new limit. Just x plus 2. Well, now if I plug in 2 there, I get 2 plus 2, I get 4. That's how it is. If you were to graph x squared minus 4 over x minus 2, you would see something that looks almost exactly like this. You'd have a line that has a y-intercept of 2 and a slope of 1. It would look exactly like this, except where x equals 2, there will be an opening. It's hard to see on your calculator where that opening is. You have to, even zooming in doesn't help. If you do zoom decimal, it works. Or if you look at the table, you'll notice that where x equals 2, y is, it's either open or error. I think it says error. Okay? Always look to factor. I know you might see a limit that involves trig. Okay? Let's say the limit is probably going to be 0. And let's say it's sine of 2x over x. Okay? There were a couple of trig rules for limits that you learned. One was that the limit as x approaches 0 of sine x over x equals 1. And the other one involved cosine. I think it was 1 minus cosine x over x equals 0. I think that was the rule. It seems to me that this one's coming up more often in the review questions that you've been seeing. So if you see something like that, and then you look here and it's like, okay, well, I can relate those two somehow, but what do I need to do? And this is one of those problems that's coming up enough that you might see it on your exam. That's, if only I had another 2 here. Here I'm trying to make a dotted line. If this was a 2, then I could easily do this because this and this would be equal. And you can actually make that happen. You can put a 2 here if you also write a 2 up here. Because what you're doing is multiplying the top and the bottom by 2. 2 halves is 1, so you're multiplying the whole thing by 1. Now let's rewrite this. You've got sine, why am I writing cosine? Still haven't done it yet. We're doing a limit. As x approaches 0, now you've got sine of 2x over 2x. Since those are the same, that whole thing is going to be 1. And you've got times 2 on the outside. This thing will become 1 times 2. This becomes 1 times 2 equals 2. A couple more. Number 10. What graph are they giving you? I've seen a couple of problems where they will ask you questions about f of x, and they will give you an f prime of x graph. Be careful. It's really easy to miss. You might see the graph, you might see a word like increasing, and you might think, oh, okay, I know what's going on. But if they're giving you f prime of x, and they're asking you questions about f of x, it's a different story. They might give you something that looks like this, and then they might have labeled here, oh, by the way, y equals f, or I should say, yeah, this value is f prime of x, okay? This is f prime of x here.